So remember that ln is just equal to log base e. That's all that is. So in order to evaluate, for example, ln of 1 over e squared, that would be the exact same thing as taking the log with the base e of 1 over e squared. So you can do e to the x is equal to 1 over e squared. Okay, and then once you're here, well, you want to get the bases the exact same, right? And how can you do that? You can use algebra now. So now you can rewrite it as e to the negative 2. And therefore, since the bases are the same, we have x is equal to negative 2. This is another example. So now we have ln of root e. Now we can rewrite this as e to the x is equal to root e, right? And then this is exactly the same as the first example we did with root 3 and 3. So now we just square both sides and we get e to 2x is equal to e to 1. Therefore, x is equal to 1/2. So it's the exact same idea as a log, basically. The only difference is that it's log base e. So there's just no difference. So now, when we're faced with exponents, for instance, such as this, well, this is what we can do. So firstly, we have log base 3 of 3 to the power of 5. So first, we can use the log rule where the 5 goes down. So we bring the exponent down. So whenever it's log base something of like an x here is 3 to the power of 5, right? If this part, like the what's being evaluated, has an exponent, you can bring the exponent down. So that would just equal 5 log base 3 of 3. And then now you have 3 to the x is equal to 3. Therefore, since x is equal to 1 here, since log base 3 of 3 is equal to 1, we just have 5 times 1, which is equal to 5. Now, for this one, we have a new log rule. And the log rule is if the base of the exponent, so we have 3 to the power of log 3, 5. Okay? So if the base of the exponent is equal to the base of the log, which is taken to the power of, then they cancel out, right? And why do they cancel out? Well, let's think about it. 3 to like the 1 would equal to like 3, right? That's why they would just cancel. So they just do this, and all of a sudden, the 5 goes down here. And I know that seems confusing, but this is just something you need to memorize, okay? So just memorize all of the log rules and it will make sense. So this would just therefore equal 5. And then here we have 10 and then 2 times log base 10 of 5. So for this one, since it's log base 10, right, we know that, then these would also cancel out. And the log just disappears. And then everything just goes down, okay? So now we just have 2 times log 10 of 5, right? And you already know that the log 10 cancels. But before we do that, we have to use a log rule where, remember, here we brought the exponent down. Now here, since this is multiplied by that, we have to bring it up. So it's a reverse. So always do that before, okay? Because we're evaluating this entire expression. So now it would be log base 10 of 5 to the 2. But we already know that since everything was raised to the power of 10, or 10 was the base and it was raised to the power of log 10, 5 squared, then these cancel. Now we just have 5 squared. And 5 squared is equal to 25. And that's how you use the log rule. So to evaluate e to the power of 2 times ln 5, you use the exact same steps as you did with this question. Remember, the only difference is ln is just log base e, right? So we can do e So we can first bring the factor that's multiplied by, so it's 2 times ln 5. We can bring this over here. Now that's equal to 2 times ln 5 squared, right? And since e and ln have the same bases, like e we call it an exponential base, right? Same with 10, same with 3, then they can cancel because they have the same bases for the exponential and for the log, or ln. So since these two cancel, that just equals, well, 5 squared. And 5 squared is equal to 25. Therefore, that would be your answer. So now that you understand ln and you understand two of the basic log rows, I'm going to go over like the rest of the log rows now, okay? And these are very important for solving algebraic equations and evaluating. So we already went over two of them. The first log rule that you already know is if we have a log and then the x, which is 3 here, is raised to the power of something, here it's 3 to the power of 5, you can just bring down the exponent. So now it would be 5 times log 3 of 3. Does that make sense? And you just have to memorize all of these rows, okay? There's not really like any like logicking it out. It's just memorize it. So yeah, remember, just bring down the 5 and just multiply the exponent by the actual log and get rid of the power. So just bring this down. Okay, that's all. And then your second log rule that you know is that if there's a number, let's say the number is a, here it's 3, and it's raised to the power of a logarithm with the same base, basically, because this would be the base of the exponential, and this would be the base of the log. If they're exactly the same numbers, then they basically just cancel out. So 3 to the power of log 3, 5 would just equal 5, okay? And then here would be both of these rules combined. So now we have 10 to the power of 2 log 5, but instead of bringing the exponent down, you would bring the 2 up, right? Because that would equal the same thing. So we know that it's going to be 10 to the power of log base 10 of 5 squared. And 10, 10 cancel because they're the same thing. So now you just have 5 squared. And 5 squared is equal to 25, right? And then that's the same thing here for ln. So we have e to the power of 2 times ln 5. Bring up the 2, right, instead of down. Then since it's e to the power of ln 5 squared, we know ln is equal to log base e. So they would cancel, right? Because same bases. And therefore, that would just equal 5 squared, which is 25. So that's those are your first two log rows. Now, your third log row is going to be this one. So it's log base a of x of y, x times y, is equal to log base a of x plus log base a of y. So if you have a logarithm, and let's say it's like what it's being taken of is multiplied, here it's e squared times 4, right? So it's log base 2 of e squared times 4. Then you can split it up, basically, just like what this log row says. So instead of that, you can write it as log base 2 of e squared plus log base 2 of 4. So you can just basically split it up like that. And then here, your fourth log row, this is called the division rule or quotient rule. So instead of adding them, like in the multiplication rule, you have to subtract them now, okay? So let's say we have log base 2 of e squared divided by 4. You can rewrite this as log base 2 of e squared minus log base 2 of 4. So those are your main log rules. And also, so for this rule, it's log base a of b is equal to log base c of b divided by log base c of a. Remember, a, b, and c are just any numbers, okay? So, and also if you multiply this out, you get this, which is equal to the same thing. So either of these forms work. So just memorize this log rule. It's called the change of bases rule. So now here's an example. Let's say we have log of 2 of 7, and you want to change the base, okay? if you want to change the base, then like in an algebraic equation, for example, if you really want to change the base, you can rewrite it as this. You can just use the rule, right? Because you see how you have log base a of b is equal to log base of another number of b over log base of another number of a, and as long as they're the same in the fraction. So if you really want to change the base for some reason, right, then you can choose whatever base you want. If you want the base to be like 7, then sure. But here, I want to change the base from 2 to 4. Okay? That's my goal. I want to change the base of log base 2 of 7 to an expression where the log has a base of 4. Okay? I just want to change the base. So now, I'm just going to rewrite it as, well, this 7 is going to go here, and the base is going to go on the bottom. Okay? So the subject, which is 7, goes on the top. The subject, the base, goes on the bottom. Okay? That's it. And then you can just rewrite log of any number of 7, and I divide it by log of any number, log base any number of 2. Does this make sense? So just do a lot of practice and you'll get used to it. Okay? So remember, this, I want to change the base. How would I do that? Well, you can choose any number as the base. In this case, I chose 4, and I just followed what the rule said. All right? So here's another rule. So if we have log, and then it's a base, but the base is put to the power of something, of x, we can rewrite this as 1 over n times log base of x. So I know that seems confusing, but all I did was, since the base is put to the power of something, then we can put whatever it's put to the power of as, we could bring it here into the front, but we would write it over as 1 divided by that. Does that make sense? So it's the reciprocal of n multiplied by the entire expression, and n can now go away because we already moved it. So here is a better visualization. It's base to the power of something, of like a number. I move it here, right? So now it's n, but now you take the reciprocal of it. So now it's going to equal 1 over n, okay? This is just a rule you need to memorize. And no matter what the numbers are, it's all the same thing. So I'm going to use, here, let's say, I don't know. So if, for instance, you want to change the base to like 2, for example, like here, you have the log of the change of base rule, but let's say you don't want to do all of that, right? Like you just don't want to do all of that, and instead you want to change the base to 2, but you don't know how. So this is how the rule is actually useful. I can rewrite this as log base 2 to the power of 2, right? Because why? Because 2 to the power of 2 is also equal to 4. So these are the same, and it's an equality, okay? So now since we have this rule, right, where it states that if the base is put to the power of a number, n, right, we can bring it out and write it as a reciprocal and multiplied by the entire thing. So here we have 2, which is our n. We bring it out, and then we make it a reciprocal. So now it's 1 over 2 times log base 2 of 2. Does that make sense? And you see how we were able to change the bases without actually having to use this rule, right? We were just able to use this rule and get the base to 2, just since that's what our goal was. And this rule is quite useful when you're solving logarithmic like equations, okay? So here's the second last rule I'm going to go over. So we have log base of 1 over a is equal to, or 1 over a of b, right? So this rule states that that's just going to equal negative log a of b. So I know that seemed confusing, but we have log base of 1 over a, right? So we have log base, the reciprocal of a. So now if we want to change it to just log base of a, all you need to do is change the sign. So my goal here, okay, for this, I want to change the base to log base a of b. You don't want to have the log of reciprocal of a, right? That's your objective, your goal. So if that's your goal, then you can use this rule, which implies that log base 1 over a of b is equal to negative log a of b. Okay? So let's say I have log. So let's say I want to change the base to 2. Okay? So how can I change the base to 2? Well, by using this rule, it states that since 2 is a reciprocal, and you want to get it to 2 not as a reciprocal, then you can just write it as negative log of 2 of 4. Okay? Does that make sense? So this is your second last rule now. And yeah, let's do another one. Log of 1 over 8 of 7. That's just equal to negative log of 8 of 7. All right? And yeah, that's your second last rule. And now your last rule, finally, is going to be the equality rule. And this is probably the most simple one. So we have log base, so we have log base a of x is equal to log base a of y. That implies, this is what the rule states, okay? That implies that x is equal to y. So for this one, this entire thing is the rule. So if we have a log of something is equal to log of another number, but the bases are exactly the same, then that means, well, these are the same now. Does that make sense? So let's use this as an example. Let's say we have log base 2 of 9 is equal to log base 2 of like 4x, right? So for this, well, since the bases are the same and they're on either sides of the equation, then therefore, same bases implies from this rule that 9 is equal to 4x. Okay? And there you go. That's how you use the equality rule. And once you understand all of these rules, like these rules, for example, are pretty intuitive, right? Multiplication, just add. Division, subtract them. And then everything else, you just have to memorize and also practice a lot so you have an intuitive understanding of them. All right? And these are all of the log rules. And the reason these are important is because they're very, very important when you're solving algebraic logarithmic equations. So let's now start solving some logarithmic algebraic equations. So we have log base 2 of x plus log base 2 of x plus 1 is equal to log base 2 of 6. So firstly, before you solve any algebraic equation involving logarithms, you have to make sure the bases are the same. Okay, and if the bases are not the same, use one of the log rules to change the bases so they're exactly the same. But here, it seems like the bases are already the same. So not much to worry about there. Now, how can we, what can we do? What can we do to solve for x, right? And we have log base 2 of x plus log base 2 of x plus 1. Well, what does that mean? That means that we can use the multiplication rule, remember? So we can rewrite this as log base 2 of x times x plus 1 is equal to log base 2 of 6, right? And now we can distribute this. Now it's going to equal log base 2 of x squared plus x is equal to log base 2 of 6, right? And now, what else do you notice? Well, you notice that, hold on, the bases are equal, right? If the bases are equal, then that means that follows the equality rule, where we use the log rule, where if the bases are equal on either side of the equation, then what they're taking the log of, which is x squared plus x and 6, now they're the only things that matter now, because the log 2 and the log 2 basically kind of cancel out, right? Because if you actually do evaluate both of the logs individually, you're going to find this out. So we'll ignore that. Log 2 here here, this can go away, this can go away. Now it's just x squared plus x is equal to 6. So now, what does this look like? Well, if I move the 6 to this side, well, I have a quadratic equation now. And now, from here, you can just factor it. So that would be x plus 3 and x minus 2. Therefore, your equation would equal x is equal to negative 3 and positive 2. And that would be your answer. So the rules I used here were the multiplication rule, where I combined both of these, and the equality rule, where I disregarded the logs because they were on either side of the equation and they had the same basis. All right. And then from there, I just got a quadratic equation, and then I factored it, and then I solved for x. And that's how you solve an equation like this. So here's another algebraic equation. So we have log base 2 of x plus 5 minus log base 2 of x. So how can we solve this? Well, what do you notice first of all? Well, first of all, we notice that, well, these two are on this side of the equation, and then they both have log base 2, and on the right, we just have a 1, right? So what can we do? Well, think log rows, okay? Whenever we're not sure what to do from our prior knowledge before log rows, then you use log rows. So since bases are the same, that's a good thing, right? Because that means we can combine them and use the quotient row. And remember what I said earlier? Before you solve any algebraic equation involving logs, make sure the bases are the same. And if the bases are not the same, use a log rule to change them, okay? So we have log base 2 of x plus 5 minus log base 2 of x. What does that also equal? According to the division or quotient rule, that's also equal to log base 2 of x plus 5, all divided by x, right? And that's now equal to 1. So from here, we can use, well, what can we use? Well, what is a logarithm, right? A logarithm is just an inverse of an exponential. So since they're inverses of an exponential, we can just write this as 2 to the power of 1. And this is, I don't mean to confuse you with these terms, but at the beginning, remember last night we were working on just evaluating logs, right? This is exactly the same thing. We're just evaluating the log. So now it's 2 to the power of 1 is equal to x plus 5 over x, right? So 2 to the power of 1 is just 2, all right? So now we can just solve for x algebraically. And you already know how to solve these types of equations, right? So now we just have x is equal to 5. And that's how you solve this algebraic logarithmic equation using the quotient rule or the division rule. So we had this that was already out like that. It was already expanded, right? We simplified it using the log rule because they had the same bases and one was subtracted by the other, right? And then since using the properties of what a log is, you can just rewrite it as an exponent, right? And I rewrote it as 2 to the power of 1 is equal to x plus 5. So now it's rewritten in the exponent form. Now we just have a simple algebraic equation that you can solve on your own. And that's how you solve these types of questions. Because always remember, think, are the bases the same? If they're not, then change them. But if they are, then that's good. Next, how can I simplify it? Well, use log rows to simplify the equation. And from there, figure it out by using the properties of a log. And that's how your mind should think for every single log equation, okay? So now that you've finished solving these equations, well, we have to make sure they actually work though, right? So first of all, where do we encounter a problem? Well, here we have 2 solutions, here we have 1 solution. But we have to make sure the solution actually works, right? So here we have x is equal to 5. Is 5, well, 5 is a positive number, right? So that's permitted. But here, and you also have to check algebraically, but once you put this in your calculator, they equal the same thing. But here, we have two solutions. X is equal to -3 and 2. So since we have two solutions, well, do you remember what's not allowed in here? Well, what's not allowed is a negative number, right? Because that would be an undefined value and it wouldn't exist. So remember, log base of x, this implies that x has to be greater than 0, okay? It can never be negative. Just remember that. And it can't be 0 either. It just has to be bigger than 0, all right? And we have two solutions here. What is like less than 0 though? And what is actually greater than 0? Well, what's greater than 0, which follows this rule, and this is, by the way, it's if and only if x is greater than 0. Then 2 is greater than 0, right? So 2 is definitely a solution. But we have -3. And is -3 greater than 0? No, right? Therefore, we cancel that out, and therefore x is equal to 2. So I just showed you that just to see if you noticed this before, okay? But if that's what you were thinking, then that's good, okay? If not, then it's fine. Just remember this. So here's another example, and I already solved this, okay? But this is just something to really keep in mind. So remember that whatever you're taking a log of, right? Like here and also here, this number can never be negative, okay? And remember, x can be any number, and apparently, in order for this equation to be true, x is equal to 1, right? So if you put in 1, then you get 2 minus 1, and then you have 1. So those are both positive numbers, which is good, because the inside of this must be a positive number, okay? But if you put in 3, for example, if you got like a solution x is equal to 1 and x is equal to 3, well, x is equal to 3 would imply that 2 minus 3 is -1. So log base 2 of -1 doesn't exist. It doesn't work because you can't take a log of a negative number, right? And even though here it works, even though 3 would work here because it's positive, here it would not work because it's 2 minus 3, right? Which is -1, and that doesn't work. Therefore, your only solution should be x is equal to 1, okay? It should only be the solution that makes this positive, okay? And if you really want to check, just plug it back into your calculator. But yeah, that's how you use the log rules to solve algebraic logarithmic equations. And yeah, remember all of the log rules, because what I went over is just all of the fundamentals of this entire logs topic, okay? This logs topic, the fundamentals of this are based off of these log rules and how you use them to solve these algebraic equations, all right? So finish the basic equations first, such as this, right? Just do these first. And actually, before you do that though, also practice the rules, all right? Just go over here into your logs thing, and then just keep practicing like these rules. There's like a worksheet here. Just practice and practice them until like you're very, very comfortable with them. And after that, solve these basic logarithmic equations. And yeah, I know at first it's going to be like a struggle to like intuitively understand like which rules to use, but if you practice them beforehand, that shouldn't be a problem. So yes, do log rules, practice them because you're going to be applying them to the log equations. And then after that, also remember what solutions are actually allowed, right? And the only solutions that are allowed are the solutions that make the inside of the log a positive number, okay? And that's all for now.